We're surrounded by this amazing technology every single day, but have you ever stopped to wonder how it actually works? Well, today, we're going to find out. We are pulling back the curtain to see how computers really think, taking a journey all the way from the apps on your screen down to a single tiny switch.
Okay, so let's just start with something you probably do dozens of times a day. You see an icon, you click it, and poof, an app opens. It really does feel like magic, but of course, it's not. It's actually this incredible chain of events all happening at lightning speed. So the big question is, what is really going on in there?
To get to the bottom of this, we've got to peel back the layers, kind of like an onion, starting from the outside in. And first up is the software. This is the digital world you see and interact with. The programs, the browsers, the games, all of it.
And this diagram? This is basically our roadmap for today. On the very outside, you've got the application software. That's your browser, your word processor, all the stuff you use every day. Right underneath that, you'll find the system software, like your operating system, which is basically the manager of the computer itself. And then right at the very core, you have the physical hardware. We're going to travel through every single one of these layers.
So, what even is software? Well, at its heart, it's just a set of instructions. When you click that icon, you're not just opening a program. You're telling the computer to follow a very, very specific recipe of commands. That recipe is the software. It's what controls the whole shebang and processes all the data you create.
But with all these different programs running, you can imagine things could get pretty chaotic, right? So, who's in charge? Who's the boss? Well, let's move one layer deeper and meet the conductor of this entire digital orchestra, the operating system.
Your OS, whether it's Windows, Mac OS, or Android, is the ultimate master manager. Just look at all this. It does everything from organizing your files and folders to sharing out the computer's memory so different apps don't crash into each other. But most importantly, it's the translator that allows the software you use to actually talk to the physical hardware. Honestly, without the OS, your computer is just a box of useless parts.
All right, we've talked about the software layers. Now it's time to get physical and look at the actual hardware where all this action takes place. Let's talk about the computer's brain, its memory.
Now, what's really fascinating is that computers have two main kinds of memory, which is a lot like how our own brains work. You've got primary memory, which is like your short-term memory. It's super fast and holds what the computer is working on right now. And then there's secondary memory, which is like our long-term memory. That's where all your files, your photos, and your programs are stored safely, even when the power's off. And the two main players in that primary short-term memory are RAM and ROM. Think of RAM, or random access memory, as a temporary notebook that you're scribbling in while you work. As soon as you close the notebook or turn off the computer, those notes are gone. ROM, or read-only memory, is totally different. It's more like the printed instructions at the very beginning of that notebook. It holds the permanent, absolutely essential instructions for just starting up the computer. And that stuff isn't erased when you shut it down.
Okay, so we've got software giving instructions and we've got hardware, like memory, to carry them out. But how does this chunk of metal and silicon actually process information? This is where we get to the core secret, the native language of all computers, binary.
Right, so forget all the numbers 0 through 9. A computer only understands two states, on and off. We represent this with just two digits, 1 and 0. This incredibly simple, two-digit system is called binary, and it is the foundation for absolutely everything a computer does.
So how in the world can you represent any number with just ones and zeros? Well, there's a pretty simple mathematical trick for it. As you can see here, it's basically just a process of repeatedly dividing by 2. Now, the key takeaway isn't the math itself, but just knowing that any number, no matter how big or complex, can be perfectly translated into that simple on-off language the computer understands.
Okay, we have the language, binary, but what's actually speaking it? Let's go deeper, down to the absolute rock bottom, the most fundamental level of computing, the tiny little physical switches that actually make the decisions. So, the whole thing boils down to this. The physical component that represents a 1 or a 0 is called a transistor. And I absolutely love this analogy. Think of a transistor as a tiny little traffic light for electricity. It can either let electricity flow through, that's a 1, or it can stop it, that's a 0. It is, quite simply, an on-off switch. Now, when you combine these tiny transistor switches in clever ways, you create something called a logic gate. These are the real, fundamental building blocks of computation. They're just tiny circuits that take in one or more binary inputs, a few ones and zeros, and produce a single binary output. This is literally how a computer makes a simple yes or no decision.
Let's look at a few of the basic ones. This here is an AND gate. It's very strict. It will only output a 1, or turn on, if input A and input B are both 1. If either one of them is a 0, the output is always 0. Simple as that.
Next up, we've got the OR gate. This one's a bit more relaxed. It will happily output a 1 if input A or input B is a 1. It doesn't need both. The only way you're going to get a 0 out of this one is if both of the inputs are 0.
And finally, we have the simplest of them all, the NOT gate. This little guy has only one job, to flip whatever you give it. If the input is 1, the output is 0. If the input is 0, the output is 1. It's basically a digital opposite-day machine.
Okay, now here's the part that is truly mind-blowing. One logic gate is incredibly simple, right? But your computer's processor contains billions of these transistors, forming millions upon millions of these logic gates. And by combining them in unbelievably complex ways, computers can perform every single task you can imagine, from just adding two numbers together to rendering a complex 3D world in a video game.
So how does all this low-level stuff actually come together in the real world? Well, let's look at how it builds up to something you probably use every single day without even thinking about it: data compression. All that underlying logic lets us find clever ways to make our digital files smaller and way faster to send.
Here's a perfect, simple example called run-length encoding. Instead of storing a long, repetitive string of data like AAAAA, the computer uses its logic to spot the pattern and just stores it as 5 A's. So AAAAABBC becomes 5A3B2C. It's a really simple but powerful way that the computer's basic logic helps make our digital lives just a little bit more efficient.
And there you have it. We've gone from the app icon you click on your screen, down through the operating system, into the memory, and all the way down to a single transistor flipping between a 0 and a 1. An entire universe of incredible complexity, all built from the simplest possible decision: on or off. These are the fundamental building blocks of our modern world. So the only question left is, what will you build with them?